Okay. Yes, and now we we continue with the platforms again. I would want to tell you above you see the nice poster. So Christoph gave this nice overview talk already, and he already talked about the semiconductor platform. And now John from Munich, he will continue and give you some more details. So the stage is yours. Thank you.
Christian, thank you very much. So let me just ask our technical advisor, do you hear me? Everybody hears me? Okay, then thank you very much for this great introduction, and also thanks to the organizers for daring to put together a hybrid conference. Actually, I have to say, over the years, we kind of learn how to do it, and I think you've done a wonderful job on this occasion to make it fully inclusive for everybody who's, whether they're dialing in or whether they're here in the physics centrum. It's my kind of, maybe we just can somehow get away. Can we get away that big?
Top left.
Let me try it. Okay, I think we're good now. So thank you very, very much once again. And it's my pleasure to talk then in my talk about some of the hardware platforms based on semiconductors for QR.X and the QR.X project. And you see that I've given my talk the kind of subtitle Quantum Light Generation and Spin-Photon Interfaces, because semiconductors, as Christoph said in his talk, have this property that they're capable of extremely high rates, modular components you can build which are attached to fibers. So really for sort of in the field type demonstrators, which is what we need. What they're sometimes criticized for, rightly so, is the spin qubits hosted by semiconductors tend to have rather short coherence times. But I'll try to give you a little bit of a perspective what is possible for quantum light generation. So single photons, entangled photon sources at different wavelengths. And I'll also try to give you some perspectives that you shouldn't give up yet on semiconductors for spin coherence, because there's a lot of developments and a lot of perspectives for extending the coherence time into the interesting range for quantum communications. So I'm standing here not really representing the work of my own group, but representing a community of researchers within QR.X working in this semiconductor platform. So you see them all listed here. I won't name them all, but I'm very grateful to all of them, because I sent an email a couple of weeks ago, please send me a couple of slides, and I could have spoken for 2 hours with the amount of material that they sent me. So thanks to them, and also apologies to them if I don't present the work that you sent me. It was all fantastic, but I had to make a choice. It's a very interdisciplinary, let's say, community in the semiconductor area. And I have to say, we're also supported tremendously, not just by people within QR.X, but also by various groups supported by the Quantum Futur initiative. There, for example, Kai Müller in Munich and also Toby Heindl in Berlin are also doing fantastic work which supports this network of semiconductor-based people. Now, I'm going to talk, the majority of the talk today, about semiconductor-based quantum dots and also quantum dot molecules. So maybe for the non-experts, these types of systems you see here on the, this is an atomic force microscope. It's actually an SEM image, if I remember correctly. And you see that they form when you grow two different types of material together. So an example is indium gallium arsenide on a substrate, which is gallium arsenide. And these two materials have slightly different lattice constants. And what it means is when you grow the indium gallium arsenide on the substrate, it forms little droplets. And the size of these droplets, it's a little bit like water droplets, if you like, on a piece of glass. You know, they form droplets rather than wetting the entire surface. And the free energies are minimized when these droplets have a size in the few tens of nanometer range. And that's what essentially is the workhorse since 30 years, where people have made very performant lasers, quantum devices, modulators, all kinds of opto-electronic devices for classical communications using these types of semiconductors. Now, the important property, there's many important properties, but the ones I want to just remind the non-experts of, I'm showing you here on the left-hand side a kind of energy diagram, which shows the conduction band within such a quantum dot, showing some trapping potential. And you see here a bunch of orbital states, just like the orbital states of an atom. So this might be an s orbital and some p, x, and py orbitals. The reason you only have two p orbitals, unlike an atom, is because these things are disc-shaped, they're not spherically symmetric. But nevertheless, you can imagine that each one of these orbitals can be populated by two carriers, two electrons, one of either spin. So if we excite this system and we create lots of electrons in the conduction band, and by definition, then lots of holes in the valence band, what you end up with is a series of many particle states. So here you see 4 quasi-particles, which are holes, 4 electrons in the conduction band, so 8 particles in total. And these particles are all trapped inside the quantum dot. They interact via the Coulomb interaction. And that means that if you let them all recombine, they would produce, let's say, 4 photons. And the only thing that's important for this talk and this context of this talk today is the 4 photons, they all have extremely different frequencies because of these Coulomb interactions between the particles. So because of that, just to give you some numbers, if you're a quantum optics person, you like to work in gigahertz or terahertz. If you're a semiconductor person, maybe other units. But the line width of these transitions is Fourier limited. I'll show you that. So about a gigahertz. The spacing between these different Coulomb occupancy states is typically terahertz, the thousands of line widths. And the spacing between the lowest orbital states, that's the fundamental transition here in the quantum dot, and then these higher lying orbital states, that's if you like an excited state transition, this is tens of terahertz. So that means that if you deal with a single electron hole pair in this system, that's where we get this, let's say, qubit character. It's spectrally isolated from all other excitations of the system, and therefore we can do quantum optics experiments on these things. So they behave as quasi 2-level systems, and these days I'll show you people can develop methods to isolate single quantum dots. There you see a typical device from our lab. Each one of these windows is 10 by 10 micrometers, and we've done a hyperspectral image, so you see that these false color-coded quantum dots, we can find out where they are, and we can fabricate photonic structures around them and address them individually. Yeah, and this is what many people in the community are doing. So single dots really selected for site-selective nanofabrication. And I'll show you later on how we now, or many groups, place resonators, antennas, lenses very precisely around single quantum dots to allow them to be very, very efficient. So what kind of properties do they have? Well, they have what are clearly Fourier transform limited transitions. This is a resonance fluorescence spectrum obtained by tuning a single frequency laser across the transition. The line width at these days is at low temperatures, Fourier limited. You can apply pulses of light, and if you apply pulses of light, you see what in the first glance looks like kind of classic 2-level systems interacting with light, so coherent control, Rabi oscillations. And of course, you can come with a pi pulse, and by doing that, drive the system and coherently prepare the upper level to allow it then to decay and emit a photon. You can do all kinds of things like state dressing, AC Stark effect to shift levels. And you can also, if you apply magnetic fields and work with charged quantum dots, you can also have a quantum dot which has a pair of ground states which are split, which are the spin states. They're split by the Zeeman energy. And you have then a couple of lambda systems in the quantum optics language, which means you can do things like optical spin pumping. You can prepare a spin qubit. You could even optically control the spin state of these 2 levels using driven Raman transitions. So there's lots of flexibility. This picture here shows you spin pumping within about 10 nanoseconds. So you can pump the spin into one of the 2 qubit states and prepare it optically within about 10 nanoseconds. So this is, if you like, and the basic properties, and there are many different flavors of quantum dot available within the QR.X community. So there at the top, you see the emission wavelength, and I've kind of marked in there the typical wavelengths where we are working. So we're working basically with different types of quantum dot systems. Indium phosphide, gallium indium phosphide, that tends to be in the visible. Going towards the telecoms range, you have quantum dots like indium arsenide on indium phosphide substrates, indium arsenide on strain release layers. You can make them emit up into the kind of telecoms O band and into the C band. And of course, we also have, let's say, key wavelengths, silicon vacancy, maybe tin vacancy also, rubidium. And for that, there are also gallium arsenide quantum dots. So you see, at all of these key wavelengths, we can find quantum dots which, let's say, can match specific target wavelengths, whether it be telecoms or specific quantum emitters. To show you just 2 or 3 examples, the growth partners sent me a lot of material, but I only want to show you a couple of examples. This is the kind of most commonly studied type of quantum dot, indium arsenide, gallium arsenide, emitting at around 950 nanometers. These days, you can control the height of the quantum dot with very high precision, with sub-nanometer precision, to really control the frequency they emit. This is going to turn out for molecules later on to be very, very important. And you can also control the density on the semiconductor substrate. I showed you some hyperspectral imaging where you could identify single dots. There you see a typical picture of a wafer. This is the quantum dot emission. This region here is where we take the low density, where we can isolate single dots from. So that's an example for, let's say, dots emitting around 950 nanometers. If you want to go to longer wavelengths, that you have to go to different material systems, like the indium arsenide, indium phosphide material system. For quantum repeaters, that's very important. We can now go to 1.55 microns with these quantum dots. And actually, this might sound unremarkable if you're, let's say, not from the field, but getting high quality, Fourier limited quantum dots, which are good for quantum optics experiment at this wavelength, is quite a recent development. It can now be done. There you see an example of one of these quantum dots. This is an atomic force microscope image. And this is something very important. It's the fine structure splitting of the exciton. And that's the thing which limits, let's say, the fidelity of entangled photon pair generation if you just don't do anything like Casper is doing. We'll see later on. So this is a big advance. And then finally, there are also very interesting, let's say, I wouldn't call them new approaches to making quantum dots, but strain-free quantum dots made using gallium arsenide. And this is what's called droplet epitaxy. And to give you some ideas here, these quantum dots do not have indium in. That makes the coherence of spin qubits better. At the same time, they have fantastic stability, so they don't exhibit blinking. Over here, you see tens of millisecond timescales, beautiful anti-bunching here for zero time delays, and the line widths are fantastic. So these types of quantum dots in stabilized device geometries are these days extremely important. And like I also mentioned, these types of quantum dots, they also address these important wavelengths compatible with silicon vacancy and also with rubidium-87. In terms of the electronic structure, this is a picture that if you're, let's say, working with quantum dots, you will probably understand and be very familiar with. If you're not working with quantum dots, I'd like to make you familiar with it. What it shows is the crystal ground state, where all the electrons are in the valence band, a one electron hole pair state, and in principle, there are two of those with different flavors of electrons and holes, spin up electron, spin down hole, or vice versa. And then there's what's called the biexciton state, which is two electrons and two holes. So it has this kind of ladder type quantum optical system. And because the electron and hole spins, they shouldn't talk to each other, but they do have a weak interaction. The hole is a p-type Bloch orbital. The electron is made from s-like Bloch orbitals. So they shouldn't couple via contact interaction. They do actually have an exchange coupling, and that mixes these two states here. And it results in two linearly polarized states with a slightly different frequency. And this is what we call the fine structure splitting. And what this fine structure splitting does, of course, is it provides, if you like, which path information when this biexciton decays via this cascade. You know that the polarization is also encoded in the frequency of these blue and these red photons, which come out of this thing. So that's a very important property, and we'll see some of the implications of those properties in a second. When I come to the tryons, I'll try to say a little bit about spin. There you see a typical level diagram of in a magnetic field applied along the optical direction, the optical axis. There are the two spin states, Zeeman split at the lower energy. They're connected via an optical transition to a pair of what are called tryon states, so three particles, two electrons and one hole. And they're connected via, for this particular field geometry, linearly, circularly polarized transitions, sigma plus and sigma minus. That's this situation. I showed you already an example of spin pumping on my title slide. You can basically just drive one of these two transitions and dump population in another one of the two spin states. And whenever it returns, you pump it back again. So you prepare the spin in one level. That is what's called Faraday geometry, magnetic field parallel to the optical axis. If the magnetic field is applied perpendicular to the optical axis, then you mix these spin states together. You see now we're in the X basis rather than the Z basis of the spins. And you have then a double lambda system where these transitions here then become linearly polarized. And you can use this for optical spin control. You can coherently control the spins using optical pulses. And you can do this in a few tens of picoseconds. So this is kind of very fast spin control. So let me already defend my spins in my 3-5 systems. Although the spin coherence times are microseconds, you can manipulate them in tens of picoseconds. So you have quite a lot of overhead. For quantum communication, you'd like them to be hundreds of microseconds, milliseconds, to give you the distance, of course. So that's the basic property. Let me now continue to talk a little bit about some of, let's say, the results that have been going on. Okay, so that's actually perfect timing because that was the end of the introduction. So it was a kind of natural break to allow you all to digest what I told you until now. Let's move on and now talk about some of the, let's say, landmark results from the consortium and also some of the limits. So I want to talk a little bit about what I've called here quantum limits of quantum dots. So basically, what is the current performance of non-classical light sources using these systems? So I think it's important to kind of pop up here at the beginning, what is the ideal quantum light source? Well, they should generate pure single photons. So of course, if you want to generate non-classical light, that one of these, the G20 value is as low as possible. And I'll show you 10 to the minus 4, 10 to the minus 3 is now routinely obtainable. You would like the photons to be basically pure quantum states, so fully indistinguishable. So you would like, if you make, for example, a measurement of the 2-photon Hongu-Mandel interdistinguishability, that's a very, very high quality measurement, that the photons exhibit a very high degree of indistinguishability. Moreover, if you're going to be driving via excited states, that naturally introduces jitter because, of course, you have to rely on some relaxation process before the photon is arriving. So if you want to tag the photon at the right time, resonant driving, of course, is important. And you would also like high quality materials, as I showed you, to basically reduce spectral diffusion and suppress spectral diffusion. Maybe I just tried to turn on my pointer again. It disappeared since I came back. So this is an example. Where you see nicely driven Rabi oscillations of the exciton transition. So you're seeing here measurements in resonance fluorescence, and you see nicely that the light intensity oscillates, and you can identify the power required to invert the system, the pi pulse, the pulse area, which does that. If you then take this stream of photons and you pass that into a photon correlator and measure the G2 of 0, of course, you can measure then the photon anti-bunching, which comes from this system. And the question is, when you apply a pi pulse, how good is this anti-bunching? And actually, Klaus Jürgens, together with Munich and also Kai Müller, have been looking into this in the past few years. And an example of this is shown here. So in simulations, when you apply a pi pulse and you look at the population of the excited state, you immediately drive the system up to the excited state, and then you rely on spontaneous emission to generate your photon. So you excite the system, and this happens in this simulation instantaneously. It then decays and generates your photon. Of course, in reality, what happens is the pulse duration that you use to drive the system up to the excited state is some fraction of the T1 time of the emitter. And what that does is it means that emission can take place already during the coherent driving of the system. And because of that, the maximum inversion of the two-level system doesn't hit 1. It depends on the relative, let's say, duration of the pulse used to invert the system and its relative lifetime. And this is something which has been looked at actually a couple of years ago. So there you see, as a function of the pulse length used to invert the system, the theoretical maximum, or let's say lowest G20 value that one can obtain. And you see that as you go to faster and faster pulses, the G2 of 0 becomes better and better. But this is the upper limit, and it's limited by the fact that you can have essentially during the pulse duration, if you have an emission event, you can have re-excitation again. And that means that you don't get good photon purity. If your pulse length becomes very, very long, you can have excitation, photon emission, and re-excitation. So this re-excitation process is something that you would like to suppress to get the best photon purity. And this is something we discussed a few years ago in this paper here in Nature Physics. The way that you can get around this problem is you cannot drive the system directly on resonance with the exciton, but you can drive the system, the bi-exciton cascade, via a 2-photon resonance. So for example, you have here the bi-exciton, you can apply your laser at this purple frequency, and therefore you can coherently prepare the biexciton. And this is a nonlinear 2-photon excitation. It depends on the square of the power. And because of that, you suppress the re-excitation. There's an example from our lab, but from, I think, Casper's lab and other labs, there are similar examples. So there you see the exciton and the biexciton. The driving laser here is in the middle between these two transitions at this purple frequency. And if you then look at Rabi oscillations, the Rabi oscillations are very, very clean. And if you then, let's say, look at the single photons, they're the ones I've been showing you, they're very, very clean. And if you look really at the G2 of 0, which is measured, and this is a tough experiment for a student to do, you're basically looking for no counts, which is very easy to find, of course. And you can see that driving the same quantum emitter via the 2-photon resonance, as you shorten the pulse, the G20 gets better and better. And the black data here shows the same 2-level system driven via the 1-photon resonance. And you can see that driving via this 2-photon resonance produces much better photon purity. And this is the experiment. This is the theory obtained by solving the master equation. And you can actually see that there's very good agreement between the experiment and the theory. So it sounds good. You just have to drive via this 2-photon resonance. You get very clean single photons from the system, but there's a price to pay. And the price to pay is in the indistinguishability of the photons. So this is a Hongu-Mandel interferogram showing the indistinguishability. So you see here in the middle, the usual dip telling you that you have indistinguishable photons. If I compare that's driving resonantly on the exciton. If I compare that data now with driving the exciton via the 2-photon resonance, so this is driving via the 1-photon resonance, driving via the 2-photon resonance, suddenly the indistinguishabilities is not 92%, it's 57%. And if you look at the biexciton via the 2-photon resonance, the indistinguishability is also about 60%. So under 2-photon excitation, this indistinguishability gets reduced, although the G2 of 0 got much better. So similar results are obtained for a few different quantum dots. You can take a look in this paper to find out the details of this and to show you where this comes from and what happens. Essentially, this is a simulation here done with Q-tip, which shows following a pulsed excitation of the biexciton and this cascaded decay. It shows the population of the biexciton level in red and the population of the exciton level here in blue. You can see the biexciton decays via one of these two polarization transitions into the exciton states. And if I then plot the exciton, you see it rises up as the population decays. And this causes an inevitable jitter in the time at which the photon arrives. And it's this jitter which reduces then the quality of the 2-photon interference. So what you have to do is you have to basically shorten the lifetime of the biexciton transition. And by doing this, this is showing the upper bound on what the visibility can be. So obviously by making the lifetime of the biexciton as short as possible, you can make the indistinguishability better and better. And this is something that was done. So it was shortened by applying a stimulation, a pi pulse, exactly at this frequency. So you prepare with a 2-photon excitation of the biexciton, you then drive it into the exciton. When you do that, this is the dynamic. So there's the original curve that I just showed you for biexciton and exciton population. Here, the pi pulse stimulating the biexciton comes at this particular point in time. It transfers population into the exciton. This is just the photon number, both for the exciton in blue and for the biexciton, depending when the stimulation pulse actually comes on the system. You see, if you wait a long time, it doesn't matter anymore because spontaneous emission has already taken place. And just to kind of show you then what you would calculate to be the indistinguishability, well, for short, the stimulation pulse coming shortly after the preparation, the distinguishability can become very, very high. If you look at the G2 of 0, the G2 of 0 can there be theoretically very, very low. So you can have both things, good indistinguishability and low G2 of 0. And this is the predictions of the theory. We've done these experiments. There you see the G2 of 0 with the stimulation. It's very, very nice, 10 to the minus 4, 10 to the minus 3, really. And this is the Hongu-Mandel from the same system. And you see you get a good visibility, which corresponds quantitatively to the lifetimes of the exciton that we have in the system. So it's a kind of case of having your cake and also eating it. You can get both of these metrics in the same system by driving the system quantum optically. There's experiments showing you the indistinguishabilities which were reached. It doesn't go to 1, but indistinguishabilities go up towards 90%, just like the theory predicted it would. And if you look at the intensity, you see the intensity is also twice as high as if you don't stimulate. The reason is, if you want single photons, of course, and you polarization filter, normally you polarization filter out one of these two photons, and here you can dump all of the population into one of them, so you essentially double your brightness if you can increase, let's say, if you can come short enough times with your excitation pulse. So I've just shown you some recent results from Paderborn and Kai Muller's group, and in what we've been doing in Munich. It shows quantum light emission due to coherent driving. Of course, you need nano-photonics to get high efficiency for the quantum channels as well. And for that, there's very many different approaches which are being pursued within QR.X. You've seen already in Christoph's talk earlier on, bullseye antennas. People have also been looking at solid immersion lenses made from gallium phosphide, also micropillars. And we've also been site selectively placing such antennas, I'll show you later on, onto the top of single quantum dot molecules to give you the broadband photon extraction efficiency. So the idea is, of course, you can use the Purcell effect to control the dynamics of certain transitions. You can also, in the context of spin-photon interfaces, you might need to cover, for example, both Zeeman transitions to drive some Raman transition like this. So you need bandwidth and low mode volume. To show you a few examples, this is an example from Peter Michler's group. They've been developing these very, very beautiful gallium arsenide membranes. They have in the middle of these membranes quantum dots emitting in the O band, the telecoms band. And they've been realizing membrane angular Bragg cavities. You see them up there. So there's an SEM image. Here you see in the middle a calculation of the Purcell factor for such a quantum dot ideally placed within such a Bragg cavity. And I'll show you that we can position these things around single quantum dots. You see Purcell factors which go up beyond 10. And more importantly, you see this over a rather large bandwidth. Here you see the bandwidth is of the order of 10 nanometers. Here you see the radiation pattern from this thing. And of course, matching the radiation pattern with a single mode fiber is something that one has to do. Just to give you some examples to flash them quickly, there you see single photon source emitting in the telecoms O band with, in this case, driving via the P shell, an excited orbital state. You see on the right-hand side there, the G2 of 0, which is available. Also at the same time, you see the count rates. The count rates are going up to around 500,000 or so. And you also see that the thing is still blinking, but the count rate is very high and it produces a very, very nice single photon purity. I think if you're interested in this, in these telecoms dots, please take a look at this recent publication from Peter's group last year. Other members of the consortium are going with this kind of broad bandwidth, enhanced coupling into fibers perspective. And there you can see two works which come both from Dresden and also from Hanover. This is the work from Dresden, where you see they take droplet epitaxy quantum dots, fabricate then gallium phosphide solid immersion lenses, and they can then fix these samples on the backside of the gallium phosphide solid immersion lens. And by controlling the thickness of the spacer between the PMMA spacer between the lens and the chip, they can enhance then the photon flux, which is actually emitted into the fiber. So here you see an example of a planar sample with no nanophotonic solution. There is now a sample which is has an optimally placed chip on the bottom of a solid immersion lens. And you can see here they demonstrated more than 60% extraction efficiency for photons. Actually, I heard at the coffee break they have even more now, but I don't want to steal your thunder. You can show people when you present things, Casper. And the important thing about this is if you want to generate entangled photon stairs to implement the quantum repeater protocols, this is broadband. So both of the photons from the exciton bi-exciton cascade are both extracted using these types of solutions with a high efficiency. And here you see an entanglement fidelity of above 90% with high extraction efficiency. So I think this is a very important. So high Q resonators are, of course, very, very useful for stimulating particular transitions, but very often we have control fields. We have to extract two different frequency photons. So these kinds of solutions are very important. Finally, there's work being done. This is work from the group of Fei Ding and also together with Dresden, where they've been developing both, entangled photon pairs. They can tune the frequency of the photons which are emitted. And they can also, by placing the quantum dots on top of a piezo transducer, that's what it looks like. You can also strain the crystal and by doing that, control the size of this fine structure splitting between the excitons. So there you see an example of a quantum dot whereby varying essentially a voltage applied to the electro-optical part of the device, they can shift the frequency at which the entangled photon pair source is emitting. And you can also, by using the strain, re-establish symmetry in the system, and therefore reduce the fine structure splitting below the limit of the line width and obtain then good entanglement fidelity. So I think these are some of the things which I think show very nicely how the device engineering of the semiconductor platform allows you to do this kind of thing. I wanted just to spend a couple of minutes talking about spins and molecules, because this is an area where I think there's a lot of, let's say, potential for the future. Maybe if I go back, I showed you already at the beginning of my talk, this picture, which shows a typical scenario for trions in a quantum dot, a single spin, which is essentially applied magnetic field splits the spin states into two spin levels, and you have a lambda transition to an excited state trion. In this case, for Voigt geometry, it's horizontally and vertically polarized. Yeah, that allows you to generate spin-photon entanglement by essentially preparing the spin state optically, scattering photons from the spin state, and having a polarization state, which is then dependent on the spin state in the system. People can study electrons and holes, and it turns out holes have a lot of beneficial qualities. I don't have time to discuss it in detail in my talk today. And I also mentioned optical ultrafast control of spin is possible over picosecond timescales in these systems. I think there's another very important property, and that is the ability, which was demonstrated a few years ago now by David Gashoni's group, to use such a spin here together with picosecond optical pulses to create what was in those days, at that time, linear cluster states. And linear cluster states are not useful in the scenario of quantum repeaters, but this is for one spin, which is a photon is scattered, the spin is then manipulated, another photon is then scattered to build up the size of the cluster state. What you can do is the same kind of thing with two spins, for example, in the scenario of a quantum dot molecule. So if you want to use this spin as an entangler for photons, you can build up cluster states, and the efficiency and usefulness of this depends both on the photon extraction efficiency, the coherence time compared with the control time, and these are picoseconds. The radiative lifetime, of course, is much faster. Coherence times are microseconds at present for electrons, or longer for holes. And it also depends on the number of spins which are available. And I think at this point, I'm going to just show you the data I wanted to show you. I wanted to show you a little bit about spin physics, but I have to jump over that, I'm very sorry to say. And I want to finish by showing you some results, what we've been doing with this approach towards a quantum repeater cell using quantum dot molecules. So there you should see the picture that Christoph showed you earlier on with this kind of node sends photons type approach, where essentially you require two quantum memories. The two quantum memories are entangled with the photons, which are sent to Alice and Bob. And then what you need to do is a Bell state measurement on the quantum memories in order to establish entanglement swapping between Alice and Bob in the way that Christoph described earlier on. These quantum dots have the nice ability that if you grow a layer of quantum dots, and then on top of that you grow a second layer, the second layer of quantum dots nucleate directly above the first. So you have two trapping potentials which are within 10 nanometers of each other, and each one of these things can trap one spin. So I will skip over the scheme because Christoph already discussed it, but it has this nice advantage that it preserves this square root of eta efficiency. This is the kind of scheme. So you first entangle one photon in one spin with one spin, then you entangle a second photon with the spin. After that, you make a Bell state measurement requiring you to have two spin interactions there. And you make then a bit flip. So you would like to have enhanced coherence times. And I'll show you that there's good reasons to expect significantly enhanced coherence times in these systems. So that's what you need. And our idea is then to put these together in the framework of two quantum dots, each of which is addressed using a different laser frequency, each of which hosts a spin. And these two spins can then couple with each other. And that allows you to essentially entangle the two spins and therefore perform the protocol we just looked at. Incidentally, this is nothing more than, let's say, twice the protocol for the cluster state generation that we just looked at a couple of minutes ago. So this is an example of, that's the Schwarz paper here. There were predictions already 10 years ago from Sofia Economou for doing this with 2 spins, and by doing this, generating then 2D cluster states deterministically, which are then useful for quantum repeater architectures. So you need to either take linear cluster states and fuse them together to make a 2D cluster, or you can directly generate a 2D cluster state using 2 spins in this way. So we've been fabricating these structures. I just want to give you a few examples of how far we've got. What do you expect to see in these types of systems? Well, you expect to have coupling as the electrons and holes can tunnel between the 2 quantum dots forming the molecule. There you see an example of electric field dependence in a cartoon of a direct exciton in the upper quantum dot. So that would be this kind of state, electron hole pair in the upper quantum dot. It doesn't stark shift very much as a function of the electric field because it has very little permanent dipole moment. At the same time, if you move one of the 2 particles into the other quantum dot to make an indirect exciton, this has a significant dipole moment. And because of that, when you vary the electric field, it should shift very strongly via the DC Stark effect. And of course, where they come onto resonance, if there's coherent coupling between these 2 states, they should anticross. The splitting then is dependent on the strength of the coupling. And that produces then hybridized states where the orbital states form, let's say, antisymmetric and symmetric combinations. So here I'm showing you for the electron hybridizing between the 2 quantum dots. Very important for what we want to do with the quantum repeater is the doubly charged trion. And this is a bit complicated, but I just want to show you quickly what you'll expect because we've actually seen this now. So this is my notation. So if you see a matrix like this, this is how many electrons are in the bottom quantum dot, how many electrons are in the top quantum dot, how many holes are in the bottom and the top quantum dots. So if you place 2 electrons and in such a system, so a doubly charged quantum dot molecule, these are the different basis states that you can create. And you see I've indexed their spin there. So you can either have singlet states, where both of the electrons can occupy 1 orbital in one of the 2 dots, or you can have triplet states, or you can have a singlet state where both of the electrons are in the other dot. The 2 electron states then form singlets and triplets, just as you'd expect, like the excited states of the helium atom. And if you then plot the energy diagram, fixing the energy at the triplet state, so there's the triplet state energy, these are the singlets which shift as a function of the electric field, and they should anticross when they couple together, and that produces there at this particular point in the field, a region where the triplet and the singlet have an energy gap which is independent of electric field, and it's also independent of magnetic field. So in magnetic field here, you have a splitting of the 3 triplets, and this energy gap here to first order is independent of magnetic noise and also independent of the electric field noise. So the question we were asking ourselves is, can we attach wires to a single molecule? And can we see this spectrum, which is what we need for a quantum repeater architecture? To do that, we had a round-robin experiment. So we've got samples from Bochum. They were sent to Berlin. They came to Munich, and we sent them back to Berlin, and we moved the samples around and built it up. I've managed to animate that process due to the speed of the Deutsche Post. So there's the molecules grown, in this case in Bochum. They have exactly these dimensions. So the heights are accurate to within 0.1 nanometer. They're separated by about 10 nanometers, and they have a tunnel barrier to suppress the strength of the tunnel coupling between the 2 quantum dots forming the molecule. There's the strength of this singlet triplet splitting that I just showed you. So we're aiming for something which is around about 0.1 milli-electron volts, 100 micro EV or so. Why? Because that strength will allow us to control the coupling using electric switching to switch on and off the coupling between them. We want to do that. Obviously, if that's too fast, if the coupling's too strong, we can't follow and we can't switch anything. There's some details for the experts. So it's a PIN diode with single molecules inside. And we have this nice tunneling barrier next to the quantum dots molecules, which allow us to place optically the charges inside. So how does that work? Well, this is what the band diagram looks like. We come with a laser pulse. It's tuned to one of the exciton transitions. That creates an electron hole pair, and the hole here can tunnel out. So there you see it, it's tunneling out, leaving just the electron behind. That's us creating the first electron. And then we can do the same thing again to place a second electron inside this thing. And then we have our two electrons, and we can control the energy of the two levels to allow them to couple or not couple. So this sounds challenging. It turned out it was challenging, but we managed to do it. So let me show you what the device looks like, a real device. We first send the sample to Berlin, and Stefan Reitzenstein is in cathodoluminescence finding single molecules. There's one of them. He then, around this single molecule, is writing an annular Bragg mirror. So that's an annular Bragg contact to strengthen the coupling with that single molecule. There's an example of that, and there's a picture of the device. It's actually only 2 periods of this grating. That's enough to get us about 20 to 30% coupling efficiency. He sends it then to Munich. So I've added our logo down here at the bottom. And what we do is we then etch down to make a device which contains just a single molecule with a little lens above it. There you see one of those. If you see these little rings here, that's each one of those has a single molecule underneath it. We then take that single molecule, process the diode, and we put contacts on one side or on the PN junction. So what is the back contact? This is an insulator, and there's many of these individually contacted molecules. So you see a nice molecule that's this little annular contact. Each molecule is contacted by a one wire. That's what the device looks like. And if you do then luminescence measurements on that, you can nicely see that single molecule lighting up at the end of that annular Bragg contact, and you can do spectroscopy on it. If you do spectroscopy on this thing, I can't describe in great detail, but that's what kind of thing you see. So you see all of these anti-crossings arising from this tunnel coupling that I told you about. You also see very, very complicated structures. And I want to kind of get out of jail by just showing you that actually we can find in here, by preparing the two charges, exactly the singlet triplet features that we were looking for to make the protocol. So we first demonstrated that the things were good for generating quantum light. So there you see a nice paper where we demonstrated the molecule does generate quantum light, just like the single quantum dots do. We could measure the strength of the tunnel coupling. We did this for many different molecules. There you see experimental data where you see the anti-crossing from which we get the strength of the tunnel coupling. It's close to what we hoped it would be, telling us that the samples are grown in the right way. We also then, and this is the important thing, observed this double negatively charged trion, and that's what we need for quantum repeater concepts, both the, let's say, node sense photons and photonic cluster state generation. So this is the trion state versus electric field. This is what you leave behind. That's the 2 electron state that I showed you a couple of slides ago. And the difference in energy between these two states, that's the photon energies that we obtain. And you probably, I don't know if you see it on the screen better than I see it here, the black lines are theory and the experimental data is behind. So there's great agreement between the two of them. To show that a bit better, there is, let's say, the experimental data. There is then the theory of just this double negatively charged trion, and we can exactly extract, if you look in here, we can extract, let me go back, exactly from this splitting here, from the sweet spot, the singlet triplet splitting. We find it's 720 micro EV. It should have been a bit smaller than this. It should have been 100, but this is an exponential function of the spacing between the two quantum dots. So we're currently growing samples where the spacing is a little bit larger, so we can suppress this tunnel coupling and allow us to control this molecule. So I think this is all on a good way, but I hope you can see that the ability to site selectively create antennas around certain molecules and place and connect them to wires, this is something which I think is going to be very, very useful. Finally, that's the spectroscopy. I showed you, or I claimed that we would like to deterministically place first 1 and then 2 charges in a single molecule. And actually, we've just managed to do this a few months ago. So this is an experiment where we apply 1 laser pulse to place 1 hole in the quantum dot molecule. If you place the hole in, the neutral exciton disappears and the positively charged exciton appears. If you place 2 holes in there, then you see appearing the double charged exciton, exactly like we wanted to have it. So I think we're on a good way, and I hope that at future QR.X meetings and maybe at this meeting, we can then present that we've actually built a device we can do some quantum communication with. So I'm certainly over my time, but let me just emphasize in my summary some of the things that I think the semiconductor platform really offers. I think they produce sources of quantum light, which I think are par excellence. They're really sometimes without parallels, and the quality is improving all the time. They're tunable all the way into the telecoms, O and C band. And of course, that means we don't require frequency conversion. And they can also match various different systems for hybrid approaches. And you've already seen in Christoph's presentation earlier on, of course, using other types of more performant quantum memories would be very, very useful. And these types of dots allow you to do that. So I think at that point, I should shut up and let people ask questions. And I say thanks once again for hosting me here.
Yes. Okay, then I first ask the question. Okay, which possibilities do you see for quantum technology to contribute to the success of 6G networks?
So I think actually what will be a really important technological development will be to kind of create transducers capable of linking the microwave regime with photons, which can be carried by optical fibers. 6G, I think it operates around 110 gigahertz plus, and this corresponds, let's say, to spin states which are split in magnetic fields of 1 Tesla of the order of something like, G factors corresponding to rare earths in glasses. So the kind of atoms which have that kind of spin splitting, where the two spin states are optically connected to a higher lying state, which could all even be for rare earths in the telecoms range. Yeah? So I think this kind of quantum transducer to convert between microwave regime and photonic regime is something which is going to be really important. And this will be something which is essential probably in the midterm, 5-10 years from now, when, let's say, all of these NISQ era quantum devices, superconducting quantum processors, this kind of thing come online, because at that point, those systems at some point are going to need connecting together to increase the processing power. So going from 100 qubits or few hundred qubit systems, linking them together to create distributed quantum systems. And I think at that point, these transducers will be very important.
Okay, thank you again.
Okay.